Hello, algebra students. This video is a summary of lesson 5.8. In this lesson, we will explore exponential functions and look at situations as functions. So let's take a look. We're going to kind of jump around here a little bit, and I want to start with the summary. At the end of every lesson, remember there's that orange page in your workbook that has the summary on it. And I specifically want to start here so that we can look at some definitions. So we are looking at situations in this unit that are exponential. And in each situation, there is a quantity that is considered the independent variable, and another that is considered the dependent variable. Functions exist because any value of the independent variable corresponds to one and only one value of the dependent variable. So one of our two variables determines the other. So I want you to think about that. Let's reflect back to first semester when we had a function written as f of x equals 2x plus 3. What did I need to do if I tell you that x equals 3? We can take that value of 3 and put it in for x, and that 3 determines what our f of x will equal. So our x determines the y. All right, so x, or the horizontal, is our independent variable, and our dependent or vertical variable is the dependent variable. And that matters. So as we go through and look at some situations, think about which variable depends on the other. Okay, in every situation we look at, we're going to have at least two variables, and one of them will depend on the other. So let's look at one of those situations. Let's do a science experiment with moldy bread, shall we? So Claire noticed mold on a slice of bread in a plastic bag, and that mold has an area of about 1 square millimeter. She left the bread alone to see how the mold would grow. The next day, the area doubled, and the day after that, it doubled again. So if the doubling pattern continues, how many square millimeters will the mold cover 4 days after she noticed the mold? So share your reasoning. Take some time to do that. You can pause the video here. Then we can look at different representations of this relationship. So the relationship between the area in square millimeters covered by mold and the number of days since the mold was spotted, we can represent as a table. So think about our starting value. When the mold was first noticed, there was 1 square millimeter of mold. The next day, that mold doubled. What does doubled mean? It means we're multiplying by 2. So we're going to multiply each of our areas by 2. So 1 times 2 is 2 square millimeters. Day 2, we double that again. 2 times 2 is 4. The third day, double this again to get 8. And our fourth day is 16 square millimeters. Is that what you got? And now it wants us to go through day 5. So let's do that one more time. 16 times 2 is 32. Now let's see if we can represent it as an equation. Well, we did this about a week ago. So we start with our area, our total area equals the starting value times our growth or multiplier to the power of d, since that is our variable. The number of days determines the area. Ooh, that sounds familiar. So let's take a look then at how we can use this information. We can graph this. Let's graph that equation. I'm going to type my equation into the box here. A equals my starting value of 1 times, and that's shift 8 if you're typing, and then 2, and then shift 6 to get my exponent, and then d. And that's what we're going to graph. Now, I can't see that on this, so I'm going to click and drag until I find it. Because if you notice, all these were negative numbers down there, so I just need to rearrange this a little bit. Okay, so now we can see that rapid increase in the area of mold. Now, let's write the relationship as a function. So are we going to write time is a function of mold area, or are we going to write the area as a function over time? So let's figure that out. So we want to think about our dependent and independent variables. So our two variables are d, the number of days, and a, the total area of mold. Okay, which of these depends on the other? Hopefully you recognize that the area depends on the number of days. The more days we have, the larger the area. The fewer days we have, the smaller the area. So A depends on D. So we are going to write area is a function of time. And you can write in days since we are talking the number of days. Sometimes we do calculations like this in hours or minutes. So you really want to be specific with your units. Let's look at a couple more examples and see if we can't identify the independent and dependent variables. Now, these are all situations we saw earlier this week or last week. So in a biology lab, a population of 50 bacteria reproduce by splitting. Every hour on the hour, each bacterium splits into 2 bacteria. So let's think about that. What are the two variables? We have two very specific things that we are identifying. We have the number of bacteria, and we have hours. Okay, so we have the number of hours, and we have the total population of bacteria. Which one depends on the other? Yeah, the more hours, the greater the population. So the number of hours gives us the total of population. So if I use our sentence, we could say the population is a function of time in hours. How about number 2? Every year after a new car is purchased, it loses 1/3 of its value. So we have some time in years, and we have the value of the car. Which one depends on the other? Yeah. The value is a function of time in years. A lot of the time when time is involved in our problem, that will be your independent variable. So you really want to think about that, use that as a clue for how you view the rest of these functions. Let's go back to that summary. So here we had defined our dependent and independent variables. And I just want to review this. Suppose T represents time in hours and P is the bacteria population T hours after the bacteria population was measured. For each time T, there is only one value for the corresponding number of bacteria. So we can say that P is a function of T, and we write this as P equals F of T. So that's our shortcut for those blanks we filled in. If there were 100,000 bacteria at the time it was initially measured and the population decreases so that 1/5 of it remains after each passing hour, we can use function notation to model that bacteria population. So instead of using P over here, we're going to use F of T because we know that P, the population, is a function of time. And then we have our starting value times our multiplier to the power of T. Okay? So in the form of A times B to the T, that is the same as in previous equations, and we can generalize that. It's our starting value times our multiplier to our independent variable. Okay? Go ahead and write that down. So our dependent variable is equal to the starting value times the multiplier to our independent variable. And that is lesson 5-8.